So this is my theta D, which means this is my desire, and this is my output theta. Clearly, my controller over here is a P controller. And my pole over here, my system over here, though it's a second order system, but it's actually a two first order system combination, right? So we want to know how the rule locus is going to look like. So we can start from open loop system. How many poles we're talking about for the open loop system? 1 or 2? 2. They are s equals to what? 0 and negative 1, right? I'm going to draw it over here. So I have a pole over here, 0, and the other one I'm going to have over here that is negative 1. And that's my open loop. My closed loop transfer function, clearly, it is going to be 1 plus k over s plus 1, and k s plus 1. So it is going to be s squared plus s plus k, and the numerator over here is going to be k. Is this a first order system or is it a second order system? It's both. Okay? Because if your k is too small, it remains as a first order system. Let's say my k is. That's k equal. Because over here, my s, my poles, roots. We are having my s equals to what? 2, negative 2, negative 1, plus minus. Right? So it is going to be negative 1/2 plus minus 1/2 or minus 4k. Is this part over here always complex number? Only when k is greater than 0.25. This one is going to be complex number. Is that right? So let's say if this one over here, is there anything easy for us to? 0.6? No. 0.4? 0.04. So this one over here is going to, 0.09. 0.09. So this one over here is going to be right. So this one is going to be what? Come on. 0.8. 0.8. So 0.8 divided by 2 is 0.4. So this is a 0.4 and negative 0.1, right? So the pole is going to be located over here and over here. So my k increase. This one we know this is k equals to what? So when I say my k is increasing from 0 to 0.09, it's moving towards to this direction, and this one moving towards to this direction. Everybody with me? So if I have my k over here equals to 0.25, what happened? This part over here becomes what?
0.
0. So how many poles I have? I still have 2. Where are they? 1? No. Minus 0.5. There are 2. The P1 and P2. They are both at here, which are going to be here and here. So we know it's going to be moving to this direction. So far, any question? I'll use red. I'll use blue because it's clearer. Right? If my k is greater than 0.25, what happened? Do I still have real poles, or the poles becomes complex ones?
Complex.
So when they are complex ones, where are they going to move to? One up and the other one is down. But the key is the real part of the pole remains the same, which means they are always at negative 0.5. And I'll have one move up and the other one move down. Do I have any zeros in my system? Open loop 0? I don't. So since I don't have any zeros in my system, the Locus is not going to have an endpoint. It will continue going until it's infinite. So you're going to see it's going to be moving up and moving down. And this is 90 degrees. And that is because you have 180 degrees divided by 2 poles. So you have 90 moving up, the other one is negative 90 moving down. Positive 180 divided by the number of poles. That is one of the formula you guys need to remember. If you have 3 poles, the angle is going to be 60, 180 minus 60. We're going to talk about that later. It's going to be if it's 3 poles. We always divided 180 degree into the number of poles. If you have 4, then it's going to be 45, 135, 225, and negative 45. Okay? Any questions so far? So this is going to be a Locus we're going to have with k equals to 0.25. We start from k equals to 0, and as k start to be greater and greater, it's moving towards to each other. And once that they reach to a certain amount of number, they start to break up because the poles change from real poles into complex poles. When they change from real pole to complex poles, it's going to get away from real S's. But since this is second order system, we know the positive, the real part is a constant. When this one is constant, we know it's going to be a straight line. So one move up and the other one is moving down. However, at this moment, you don't really know whether this one going up or this one going up. That will be something we need to figure out later. They have Locus, but it's not going to be a sharp turn over here. It's going to be something like this and something like this. When you look into your textbook, you're going to find it out. And the other important things you guys need to remember is how to use MATLAB to help us to do the Locus. So when we are doing the Locus, we are talking about the K effect to my closed loop, open loop system, right? So because we are talking about this part, so when we are doing Locus, it's going to be RLOCUS, Locus. PF R, I'll use another color. RLOCUS TF 1 1 1 0. The TF over here means how I synthesize my transfer function as an object. The Locus simply means that my K is away from everything. So when you are drawing the Locus of this system, you should use this one. K is not part of the transfer function when you are using a rule locus. Okay, I think. Okay, we haven't had homework over here. One of homework is going to ask you guys to do this. Okay, so far we're not really talking about rules. I'm just telling you how the poles are going to be moved based on different case. So if we try to do locus, they have specific formula that we can follow, and there are many small details, really, a lot of small details you guys need to pay attention to. Sometimes it's just a little bit tedious. So we're going to explain everything, and when we encounter the specific parts, I'm going to explain to you which part you need to pay attention to, okay? So for rule locus, we are having this is a very typical system we have as a closed loop transfer function. So when I'm talking about rule locus on the other side, what is actually the variable we are drawing? Which variable we're talking about? Are we talking about s or poles or zeros? No. Which part? Which is the variable that we're going to change the whole trajectory? Okay. So when we are talking about rule locus, it's actually talking about the system gains of the whole system. So it means that, of course, this is my controller. When you are dealing with those kind of things, you need to separate the variable you are interested in, which is the gain of a system, away from the overall system. Okay, so if you have this one as your, this one has something like s plus 1, s squared plus something or anything, you need to be combined together with the transfer function over here as your plan. Because when we are dealing with the rule locus, we're talking about the change of trajectory related to the gain. So gain is the only variable, which means when you are dealing with those things over here, Kp specifically over here need to be separated away from your controller. Okay, when we are dealing with those kind of things. So in other words, I know my closed loop transfer function in this case is going to be Kp, G, C, GP, 1 plus G, KP, GC, GP, and H. Normally, when we are dealing with H, this one is close to 1. So this one is just 1. And we are actually trying to get G, 1 plus G of H. We are combining those things as a chunk and try to keep H as 1, but this is something we really taking care of, okay? So when we take care of this one, what I really have is 1 plus GH equals to 0, or GH equals to -1. Because we're talking about the characteristic equation over here. So when I try to identify characteristic equation, this is going to be the equation we're going to use. And if you just put the 1 on the other side, this is going to be something we're going to look at. right? When we are looking at complex systems, there are two things you guys need to remember, and it's going to be valid from now on till the end of the semester. When you are talking about complex systems, one is going to be magnitude, the other one is going to be phase. Magnitude is taking the absolute value equals to what? 1. When we are talking about the phase, it is going to be arctangent imaginary part divided by real part. Why is that? Because keep in mind, I have real, I have imaginary. This is y value, this one is x value. Tangent theta equals to y over x. When we are dealing with S domain, this is the y-axis is what? Imaginary. Real part is, the x is going to be my real part, which means my theta is going to be arctangent imaginary over real. That is a phase when we are dealing with complex numbers. So there are two things you need to remember. One is magnitude, the other one is phase. And combine those two things together, you are describing the transfer function of the system. It's going to be in Locus, it's going to be in frequency response and Nyquist plot that we're going to talk about in topic 8. We're going to take a break, and when we come back, we're going to move on.